Mutual induction. Whenever there is a change in the magnetic flux linked with the coil, there is also a change of flux linked with the neighboring coil, producing an induced EMF in the second coil. This phenomenon of producing an induced EMF in a coil due to the change in current in other coil is known as mutual induction. P and S are two coils placed close to each other. P is connected to a battery through a key K. S is connected to a galvanometer G. On pressing K, current in P starts increasing from 0 to a maximum value. As the flow of current increases, the magnetic flux linked with P increases. Therefore, magnetic flux linked with S also increases, producing an induced EMF in S. Now, the galvanometer shows the deflection. According to Lenz's law, the induced current in S would oppose the increase in current in P by flowing in a direction opposite to the current in P, thus delaying the growth of current to the maximum value. When a key K is released, current starts decreasing from maximum to 0 value. Consequently, magnetic flux linked with P decreases. Therefore, magnetic flux linked with S also decreases, and hence an EMF is induced in S. According to Lenz's law, the induced current in S flows in such a direction so as to oppose the decrease in current in P, thus prolonging the decay of current. Coefficient of mutual induction. IP is the current in coil P and phi S is the magnetic flux linked with coil S due to the current in coil P. Therefore, phi S is proportional to IP, or phi S is equal to MIP, where M is a constant of proportionality and is called the coefficient of mutual induction or mutual inductance between the two coils. If IP is equal to 1A, then M is equal to phi S. Thus, coefficient of mutual induction of two coils is numerically equal to the magnetic flux linked with one coil when unit current flows through the neighboring coil. If ES is the induced EMF in the coil S at any instant of time, then from the laws of electromagnetic induction, ES is equal to minus d phi S by dt is equal to minus d by dt into MIP is equal to minus M into dIP by dt. Therefore, M is equal to minus ES by dIP by dt. If dIP by dt is equal to 1A S raised to minus 1, then M is equal to minus ES. Thus, the coefficient of mutual induction of two coils is numerically equal to the EMF induced in one coil when the rate of change of current through the other coil is unity. The unit of coefficient of mutual induction is Henry. 1 Henry is defined as the coefficient of mutual induction between a pair of coils when a change of current of 1 ampere per second in one coil produces an induced EMF of 1 volt in the other coil. The coefficient of mutual induction between a pair of coils depends on the following factors: size and shape of the coils, number of turns and permeability of a material on which the coils are wound, proximity of the coils. Two coils P and S have their axes perpendicular to each other. When a current is passed through coil P, the magnetic flux linked with S is small, and hence the coefficient of mutual induction between the two coils are small. The two coils are placed in such a way that they have a common axis. When current is passed through the coil P, the magnetic flux linked with coil S is large and hence the coefficient of mutual induction between the two coils is large. If the two coils are wound on a soft iron core, the mutual induction is very large.